Welcome back to the lectures on molecular spectroscopy and introductory chemistry. In this short lecture, let us look at the rotational and vibrational line intensities from an elementary point of view using the Maxwell-Boltzmann statistics. It was mentioned to you some lectures ago that there are three parameters which are of importance in any study using spectroscopy, namely the line positions, which are dealt with by quantum mechanics, the line intensities, which require both quantum mechanics and also statistical mechanics, since we deal with populations of molecular systems in different energy levels, and the third was the line width. We shall not consider the line width in this course, but let us look at the line intensities a little more closely, and particularly for the rotational microwave and infrared frequencies and transitions. Okay. Now, the basic formula or the basic prescription that you should remember is that molecules, the number of molecules in any energy state, let us assume that we have N0, N1, N2, etc. molecules in different energy levels, E0, E1, E2, etc. Okay. That is distribution in thermal equilibrium, distribution of molecules in different energy levels due to thermal equilibrium. What we need to know is the Boltzmann formula, which was also mentioned to you earlier in the course. The Boltzmann formula tells you that the number of molecules N at any given energy level E is approximately proportional to the degeneracy of that energy. Often it is written using omega of E, and the Boltzmann factor, which tells you the weighting for that number for that given energy, E by kBT. Okay. In the case of rotational spectroscopy, the molecular energy levels for the simple system of a diatomic, they are proportional to the J into, they are basically J into J plus 1. You recall the energy level formula for rotation for a given quantum number J, it is B J into J plus 1 times Hc. The quantum number J corresponds to 2J plus 1 states, which are given by different values of the projection of J on the molecular axis, and these are called the K quantum numbers, and they go from minus J to plus J in integer steps. In the case of diatomic molecule, we have the symmetry axis, which is the axis of the molecule about which there is no moment of inertia. Therefore, there is no rotational degree of freedom which would show up in that for that motion. The other two axes, which are perpendicular to the molecular axis, the moment of inertia about both of those axes are identical. Therefore, there is one moment of inertia, and that moment of inertia is built in this constant B as h by 8 pi square I c. You have already solved such problems. Therefore, what you have here is that there is only one energy level, in the sense one energy value for a given J. So, if you write Ej, it is B J into J plus 1 Hc, but there are 2J plus 1 states. Which are degenerate. because they all have the same value. And these are indicated by the wave function with two quantum numbers j and k, and the wave functions are usually written as using the Dirac notation, Ket notation. It is called the bracket notation. What you see is that the states are represented as the states j, k. And for molecular systems where the rotational quantum numbers are integers, these j, k states can be identified with specific representations through spherical harmonics. Y, j, k of theta phi, which you had come across in the case of hydrogen atom as contributing to the angular distribution of the wave function. Therefore, the molecular wave functions for the rotational states are 2j plus 1 fold degenerate, because all the states starting from k is equal to j minus 1, j minus 2, and all the way down to j minus j all have the same energy. In the absence of any external field or in the absence of any other considerations like moments of inertia being different and so on. For a diatomic molecule, the two moments of inertia are equal, the third moment of inertia is 0. Therefore, we have all the energy levels for a given j being degenerate. Therefore, what does this tell you? This tells you that if you are calculating the molecules, the number of molecules in a given energy state corresponding to the quantum number j, energy value corresponding to the quantum number j, and the number of molecules in another energy corresponding to a different value j prime, this tells you that this ratio is 2j plus 1 by 2j prime plus 1, and then you have e to the exponential to the minus the energy corresponding to the quantum number j and the energy corresponding to the quantum number j prime, the difference between the two divided by the Boltzmann constant kBt. So, this is the formula, this is what is called the fundamental formula for the calculation of elementary form of microwave intensities without other considerations like reactions and the interaction between rotations and vibrations, all those things not being considered. Pure microwave transitions of a rigid diatomic molecule, the number of molecules in any given energy state j to the number of molecules in another energy state j prime is given by the ratio of the degeneracies and the exponential or the Boltzmann factor given by the energy difference. So, what is this? If you write that, you recall that Ej is Bj into j plus 1 Hc, and Ej prime is Bj prime into j prime plus 1 Hc. And if you calculate, for example, n1 by n0, n1 meaning E1 with j is equal to 1 versus E with j is equal to 0, E0 the ground rotational state. If you do that, then this is 3, the 2j plus 1 here is corresponding to the value j is equal to 1, and this is j is equal to 0. Therefore, the degeneracy here is 1, 3 by 1, and what you have is the energy between E1 with the difference minus E1 minus E0 by kBt, and that you know is 2bhc. Therefore, what you have is 3 exponential minus 2bhc by kBt. Now, this energy 2bhc is very small compared to the factor kBt, the thermal energy, for any temperatures like greater than say 10 Kelvin, and certainly T 300 Kelvin, this energy Bhc is much smaller than kBt. Therefore, you see that the number of molecules in the higher energy state to the number of molecules in the energy state in this particular case is actually, that ratio is greater than 1. For n E1 divided by n E0, this factor is almost equal to 1 or very close to 1, therefore it is greater than 1. So, what you see in the case of microwave transition is, since the degeneracy increases as J increases, there is this accommodation of the higher energy state of the system into many more levels, all of which are degenerate, versus the accommodation of the rotational states into lower J, where the degeneracies are slightly lower. Therefore, what you see is that the number of molecules in E1 is usually greater than the number of molecules in the energy state E0, and the number of molecules in the energy state E2 is again greater than the number of molecules in the energy state E1, and so on. So, you can say n Ej is greater than n Ej minus 1 and so on until greater than n E0. Does this go on like that forever? No, it does not, because you see the rotational energy levels also increase very, very fast, because you see the lowest energy level is 0, the next one is 2b, the next one is actually 6b, 4b, 6b, and the third is 12b, and this one is 20b, and so on. Therefore, the energy gap between successive rotational quantum numbers, the states of states with successive rotational quantum numbers, the gap increases. Therefore, at some point of time the numbers start decreasing. Therefore, if you plot the microwave rotational intensity as a function of J, you start seeing for J is equal to say 0, 1, 2, 3, etc., you start seeing that, well, let us keep the 0 out of the picture. Start with 1, with respect to 0 this is some number, 2 increases, 3 the J3 increases, and so on. But after some J, when it reaches a maximum, it comes down to, it starts becoming less and less, and so on. So, what you see is that the microwave intensities are like an envelope with increasing, and there is a maximum for some value of J. And that can be easily calculated, because if you write the number density or the number for that particular J being proportional to 2J plus 1 times exponential minus Hc Bj into J plus 1 by kBt, because this is energy and the correct unit is the Hc times the B, which is only a wave number unit. So, if you have this, you want to find out what is the value of J for which the number is maximum. You can do a simple calculus by taking the derivative of the numbers with respect to J and then set that equal to 0. You know, it is an approximate calculation. J is not continuous, therefore, you know, to take the derivative does not make much sense, but to get a feel for this, the energy levels gaps are still very small compared to thermal energies. Therefore, if you take a derivative like this, you can see that immediately this gives you the following, that the number density gives you, the derivative is, if you take the derivative of this, it is 2 times e to the minus Hc J into J plus 1 by kBt. That is the first term of the derivative. The second is the derivative of this term, which if you take, it is minus 2J plus 1, and this will give you the expression e to the minus Hc B J into J plus 1 by kBt times this derivative, which is 1 by kBt, and the minus sign is already here. It will give you Hc B into 2J plus 1. this is what you will get. And if you set that equal to 0, it is easy to show that the J max is approximately square root of KBT by 2HCB minus 1/2. Recall that this is if you set this equal to 0, the exponential factor goes away. So it's you can see immediately that it is 2 minus 2j plus 1 whole square into HCB by KBT, that is equal to 0, and that gives you the solution. Okay. That is the J max, the corresponding value of J is the J max, and you can see that this is the ratio. Therefore, microwave intensities actually peak for some middle value of J versus starting from J is equal to 0 to some other value J. What about the infrared intensity? For a diatomic molecule, there is no problem because all vibrational states are non-degenerate, single vibrational states. The degeneracy is 1. Therefore, in the case of vibrational motion, if you write this NV for N a V prime, where V and V prime are the vibrational quantum numbers for two different states, for states with two different states, and then you can see that this is nothing other than simply exponential minus EV minus EV prime by KBT. Therefore, there is no factor in front of the exponential which counters the decrease of the exponential. You can see that vibrational intensities usually are maximum for the V is equal to 0 to 1 transition, or the V is equal to 0 state itself, and then it is slightly lower and so on, and lower and so on. Secondly, with respect to microwaves and rotation spectroscopy, the energy gap is very small compared to the thermal energy, whereas in the case of vibrational states, the energy gap is comparable or even more than thermal energy. Therefore, the number of molecules even in the first excited vibrational state is going to be a lot smaller fraction of the number of molecules in the ground state. This is not so in the case of rotations. In the case of rotations, a large number of J values are populated fairly well, whereas in the case of vibration, unless the vibrational energies are very close to each other, most molecules will be at any given temperature in the ground state, and fewer in the first excited state, and even fewer in the second excited state. Therefore, you can see the drop in the intensity very, very directly. So these are the things that you have to keep in mind in observing the intensities, and also some of the spectra that I will show in one of these lectures or through the lecture notes. We will continue this with the spectroscopy of the microwave spectroscopy of polyatomic molecules in the next lecture. Until then, thank you very much.